I would like to call Professor Nektarios Tavernarakis, the chairman of the board of directors of FORTH, to make a welcome speech.
Good afternoon, dear Professor Spergel, dear Professor Kylafis, dear colleagues and friends. On behalf of the Foundation for Research and Technology, it gives me great pleasure to welcome you to the 2024 Kylafis lecture. I would particularly like to thank Professor David Spergel, who agreed to deliver this year's lecture on the current state of cosmology. FORTH and its Institute of Astrophysics have established the Kylafis lecture series to honor Professor Nikos Kylafis for his instrumental contributions and enduring commitment towards the development of the astrophysics research in Crete and in Greece in general. The establishment of FORTH's Institute of Astrophysics a few years ago came as a culmination of these efforts. Nikos was a driving force towards the creation of the Institute. Achieving this ambitious objective was not a linear process, and it was through Nikos's perseverance that eventually came to fruition. I remember vividly our long and spirited discussions about how to proceed effectively, and our frequent visits, of course, to petitions to ministers and government officials, convincing them about the need and indeed the added value of having a frontier research institute on astrophysics in Greece was an arduous and protracted struggle. From the very beginning, special emphasis was placed in creating the new institute based on the same principles and terms of excellence that all FORTH institutes and activities abide to. In point of fact, the institute is already thriving, with 5 of its members having secured prestigious and highly competitive ERC grants. Now, aiming to foster and further facilitate the pursuit of excellence, FORTH has undertaken several concrete initiatives, including the now long tradition of the Onassis lectures, attracting Nobel laureates and outstanding scientists from all over the world. We have also introduced the intramural FORTH Synergy Grants and the FORTH Research Excellence Award, among other such initiatives. The Kylafis lecture is coming as a worthy new addition in this roster of focused activities. In closing, I would like to congratulate the Institute of Astrophysics and its director, Professor Vasilis Harmandaris, for maintaining the course and organizing a lecture for the 6th time this year. I would also like to thank all of you for being here today to hear about the current state of cosmology and the exciting developments in astrophysics by Professor Spergel. And with this, I would like to finish this short presentation by giving professors the symbol of FORTH. This is the list of professors. You can actually see the original museum, the development museum Heraklion. It's not been deciphered. There are some people who say that we have actually deciphered it, but not officially yet. There's no published record of it being deciphered. And it represents the struggle, the efforts to really find answers to the unknown and decipher nature geometry. So with this, thank you very much for being here again. And I will now leave it to Vasilis and Nikos to introduce you to the audience.
Thank you.
I think I can, we can shout, so no problem.
Okay.
Thank you.
First of all, I will say that, Nektarios was not very accurate. This is the original disc of Estes, that it's offered to the president of the Simons Foundation. We put a copy in the museum that you will check on Monday. So, dear Professor Spergel, dear colleagues, I'm really excited to welcome you to this 6th lecture. And as Nektarios mentioned, this lecture is in the honor of Nick. And under the auspices of the lectureship, a distinguished theoretical astrophysicist is invited annually to Crete and FORTH for a brief visit. And the Institute of Astrophysics anticipates that the Nick Kylafis lecture is a combination, the Nick Kylafis lecture in combination with the beautiful weather and food of the island of Crete, will attract and continue to attract distinguished astrophysicists in Crete who will inspire with their presence the next generations of scientists trained here in the Fourth and the University of Crete academic ecosystem and communicate to the wider scientific community the latest achievements in the rapidly evolving field of theoretical astrophysics. Moreover, it is one of the very important elements contributing to the future success of our young Institute of Astrophysics, that is building a tradition as well as honoring those who contribute to the success. So on behalf of all of us at the Institute of Astrophysics, I would like first to thank Nick for offering us this important opportunity to make this achieving this challenging goal. And this year we have the pleasure and great honor to have with us as the 2024 lecturer, the distinguished Professor David Spergel, who is president of Simons Foundation and also Charles Young Professor of Astronomy Emeritus at Princeton. It should be mentioned that from 2016 until 2021, Professor Spergel was the founding director of the Center for Computational Astrophysics of the Flatiron Institute in New York, which is supported by the Simons Foundation and resembles in structure Forth, but with a slightly larger annual budget. Professor Spergel is internationally recognized for his seminal contribution in theoretical astrophysics and cosmology, in particular for the calculation of key parameters determining the formation and the evolution of the universe, as well as the nature of dark matter. He has published over 400 refereed papers, which have received over 130,000 citations. And numbers aside, he has received numerous of highly prestigious awards, including the Helen Warner Prize of the American Astronomical Society, the Shaw Prize of Astronomy in 2012. This is well-known as the Nobel of the East. The Danny Heinemann Prize of Astrophysics, again from the American Astronomical Society, and the Breakthrough Prize in Fundamental Physics in 2018. Professor Spergel is also a member of several prestigious academies, such as the National Academy of Science and the American Academy of Arts and Sciences. And if this was not enough, he was also selected among the top 25 most influential space scientists from the Time magazine in 2012, as well as among the 10 most important scientists in 2024, according to the journal Nature. And without further ado, I would like to welcome David to give his lecture. Before we start, since we already know that the lecture will be fantastic, we will give him a couple of presents. So, David, so we have, well, first of all is the diploma. That's really easy. And then we have a coffee table book, which is not about coffee tables, but it's with pictures of the universe taken with our telescopes here at Kylafis Observatory. And in addition to that, even though David is an observer, a theorist, we also have a jacket of Kylafis Observatory, which is actually very nice if you jog in New York City. So thank you very much. We greatly appreciate it. And we look forward to it.
So let me begin by saying what a pleasure it is to be here. An honor to be continuing in the tradition of the outstanding lecturers that have come here to honor Nick. And also a real pleasure not only to have a chance to meet with my astrophysics colleagues, but to meet more broadly with the fourth community. And it's been very interesting because, as mentioned in the introduction, we are broadly doing something very similar in New York with the Flatiron Institute that we run, of building an institute that brings together people working across fields of science, realizing that we share a common language in many ways, and that we have a tremendous amount to learn from each other. And in that spirit, let me sort of summarize, in a sense, my lecture. I think it's always one of the things that I learned early that I encourage the young people to think about in any lecture is, what's the one-line summary of the lecture? The one-line summary is, our universe is remarkably simple, yet remarkably strange in its properties. And that over the past 20 or so years, we've accumulated a tremendous amount of astronomical evidence and data that all seem broadly consistent with what we've seen. Profound and interesting theoretical questions remain, and there are important observational challenges. And in the spirit of the lectures we heard earlier today, you'll notice that many of the measurements that I will describe require metamaterials for the lenses that we do for our observations. And that really all of the analysis we do, because it's big data analysis, draws on the techniques of data science and analysis you heard about earlier. So what I hope to do in the lecture is first, let's see, advance twice now. Review cosmology, talk about the microwave background, talk about some of the current observational tensions, and then turn to some of the efforts to look for new physics and talk about the next generation of experiments. So what do I mean when I say we have a simple and strange universe? The idea is, as you'll see, that with 5 basic numbers, the age of the universe, the density of atoms, the density of matter, the lumpiness of the universe and how it varies with scale, with those 5 numbers, we can fit all of our current observations of cosmology. So it's a simple model that works remarkably well. But it's a simple model that requires profound new physics. Atoms, the stuff that makes up us, only makes up 5% of the universe. Dark matter makes up most of the mass of our galaxy, and we don't know what dark matter is. Dark energy, energy associated with empty space, comprises most of the energy density of the universe. We really have no idea why dark energy is there. Well, I will show you observations of the origin of fluctuations. We don't know, we have ideas about inflation, but much needs to be done to understand that better. And even turning to the atoms themselves, we do not really understand why there's more atoms than anti-atoms, why more protons than antiprotons. These are all open questions. But it's a field that's been quite successful. Back in 2019, Jim Peebles was recognized with the Nobel Prize for his contributions, which which is a big piece of the theoretical work that underlie a lot of the story I'll tell today. And as he emphasized in his lectures, while we have made great progress, there are profound questions that we'd like to answer today. So let me begin by giving you sort of the big picture of cosmology. The universe, in cosmology, we start with general relativity. General relativity predicts that the universe, for a homogeneous universe, is either expanding or contracting, and what we observe is it's expanding. The universe is expanding today. It must have been denser in the past. So as we go back to the past, we start with a universe that was very hot and very dense. And as we extrapolate further and further back to the Big Bang, we reach points of very high density and very high temperature. Most of what I'll talk about today is the cosmic microwave background, the leftover heat from the Big Bang. And when we look in our observations actually look back in time. So remember, since light travels at a finite speed, as an astronomer, I am always observing the past. So we're looking back 13.8 billion years, looking back to when the density of the universe was about a billion times larger than today. The temperature was about 3,000 Kelvin. And at those densities and temperatures, the universe was fully ionized. And that's the point at which the microwave background last interacted with electrons and the rest of matter. So when I show you observations of the microwave background, you should think that we're looking back to this surface of last scatter and seeing what conditions are there. It's much like when we look at the sun. It's actually sort of a flip of looking at the sun. When we look out towards the sun, we are seeing photons that came from the solar surface, and we're inferring what goes on deeper in the interior. And we're observing the photons and information about when they last interacted. And that's what we'll be doing in the microwave background. So first, let's look at the microwave background observations. And the high-level thing I want you to take away from this, and these are maps of the sky, the upper one taken by NASA's WMAP experiment, which I was part of. And this shows the whole sky around us as a sphere. The galactic plane, the plane of our Milky Way, we cannot fully remove the contributions from dust and synchrotron. So you'll see kind of a hole in the map there where we have removed and masked that data. The figure below shows observations from Planck, which is a higher resolution experiment led by the European Space Agency. It flew about a decade later. The Planck data now has been smoothed to the WMAP resolution. And you can see first, we see the same thing. This is actually a remarkable experimental accomplishment, that we're making measurements at the level of a few microkelvin and see consistent observations. And this is true not only with the space experiments, but now let's look at the ground-based experiments. And this shows ground-based experiments from Chile, where you can get higher resolution from the ground on small scales, but you don't learn as much about larger scales in the sky because of the atmosphere. So now we've filtered the Planck maps to remove the large-scale features. And you can see that Planck and the ACT experiment in Chile at the same 143 gigahertz in this side of the figure, 217 or so on the other side, we see the same sky. We can quantify that and quantify that by comparing with our theory, by taking our map and analyzing it. Since we're looking at a homogeneous isotropic sphere, what we want to do is do analysis on the sphere. So we do a harmonic analysis and expand it in spherical harmonics. We take our temperature and expand it out in the ALMs. We then measure the angular power spectrum, the C sub Ls. And what you'll see plotted in most of the plots for the data is this combination that's roughly L squared C sub L, which you could basically view as the variance on the angular scale L, which corresponds to 180 degrees. So I introduced this because this is the language we use to express our data, how lumpy this observed sky is on a given angular scale L. What also makes things simple is the universe turns out to be remarkably simple in the sense of the fluctuations are all, as far as we can measure, the primordial fluctuations are Gaussian random phase. That means that all the information is described in the 2-point function. There's no information in the 3-point function, 4-point function. The maps are completely Gaussian. That's about the simplest random function you can specify beyond constant. So it's a remarkably simple universe. When we look at our observations, what we're seeing, and here we'll turn to our theory, is the behavior of what we call adiabatic density fluctuations. So what do we mean by adiabatic? We mean that where we see that the ratio of atoms to dark matter, the ratio of atoms to photons, of protons to electrons, everything is constant. The universe over there has the same composition as the universe there. So it's a uniform composition universe with variations in density being overall variations. If there's more density here, that means there are more electrons, there are more protons, there are more photons, there are more dark matter. Density varies together. There's no composition variation. So that's the simplest case. And what happens when you have variations in density, you also have variations in pressure. We can now do that experimentally. That was a pressure variation. You heard it generate a sound wave, and those sound waves propagate. And when we look at the observations, the theme of, in a sense, the rest of this lecture is observing sound waves in the universe. And when we look at the predictions of the model, and here we're looking at variations in temperature, polarization E, and polarization, and these are measurements of the 2-point function, you'll see these sound waves propagate and produce characteristic signals in outer space, these acoustic peaks with predicted negative peak on large scales of TE and the predicted patterns of temperature and polarization. And we will go look for these in the data, and it is these observations that tell us about the fluctuations. And we can go look at this data and infer the basic properties by looking at the highest properties. So we do this in the context of how sound waves behave in the presence of gravity. As I noted earlier, this was all theory that's been understood really for over 40, nearly 50 years, with work going back to papers by Jim Peebles, Rashid Sunyaev, and Yakov Zildovich. And today, we're achieving better than 0.1, actually 0.01% today, when people have compared codes in how we predict the observations. And let's compare this now to the observations, and first just start out by emphasizing at some level it doesn't matter which set of observations from which experiment I compare them to, because all the observations are getting consistent results. And here's sort of a quantitative comparison of this. So the red curve shows measurements where we cross-correlate the Planck measurements at 100 gigahertz with the Planck measurements at 217 gigahertz. The black points show measurements from Planck cross-correlated with WMAP. And you can see that as a function of, mode by mode, they're seeing the same signal across the sky. Planck is more sensitive so that the curve has smaller error bars, but you're seeing a consistent story. And when we compare this to the large scale data or the temperature data, we're seeing a very consistent story. Here, the curve is a theory curve with our 5 basic parameters that we fit to the data. And the points are the measured points from experiments. Here we're showing it without Planck. We actually took the data, we fit it to the Planck measurements, we got the parameters. We then took other data sets in this plot. This is the WMAP data in blue, the data from Chile in green, and from the South Pole in red, and we're seeing a very consistent story. We look not only at temperature data, but polarization data. As you know, from when you put on sunglasses on a sunny day at the beach, light is polarized. And the reason you put on sunglasses like this, not like that, is not both because you don't want to look like an idiot, and because the glasses are polarized so that they block light reflected off of the ocean. And when sunlight comes off the ocean, it tends to come off at, if the ocean's here, it comes out in this polarization. So your sunglasses block the scattered light off the ocean or the scattered light off the sky. And that's why you see more clearly with sunglasses on a sunny day. So if you observe polarized emission, you're directly observing the last scattering. And polarization is a headless vector on the sky. We can decompose polarization into what we call E modes and B modes. E modes do not have a sense of curvature, and we expect the E mode pattern to be correlated with the temperature pattern here. You can see the variations in temperature shown as red and blue, and you see how E modes scale that way. Variations in density generate only E modes. Gravitational waves, which we'll turn to later, generate both E modes and B modes. So it's observing both of these that are of current interest. When we look at our predicted pattern of temperature and polarization fluctuations, variations in density and pressure predict a very characteristic pattern. So what you see here, this is an analysis of the Planck data. Always have to remember which one is theory and which one is data. Okay, the bottom is theory, and the bottom shows what happens if you take the microwave background observations and stack them on top of all of the cold spots in the map. And this shows what happens. So these are stacked on cold spots, these are stacked on hot spots, and what you see in the sky is this characteristic pattern set up by the sound waves. So we start by creating a region with more dark matter and more baryons. That's called the sound wave. The dark matter doesn't move. So this cold spot's created by having a region that has an excess in dark matter. Equipotential well created by the dark matter, you have to climb it. The sound wave moves out. The sound wave contains electrons and protons and photons. As the sound wave moves out, travels for about 380,000 years, covers of order 300,000 light years, and that's the radius here. So this hot ring around the cold spot represents a region that has excess photons and electrons and protons. And I can actually read the basic parameters of the universe off this plot. By looking at the relative amplitude of the hot ring to the cold center, that gives me the ratio of baryons, protons, electrons, neutrons, to dark matter. So I can measure the density of the universe. The radius of the ring and projection on the sky, well, I know how far the sound wave has gone. I have a ruler that nature holds up to me called the acoustic distance, which we'll use later as we look at the galaxy observations. That gives me a measurement of the distance to the surface of glass scatter, so I know how old the universe is. And by measuring the amplitude of these hot and cold spots as a function of scale, I can measure the lumpiness of the universe as a function of scale. So this is, can read all of this off the picture. And there's a distinctive polarization pattern and how it correlates with temperature that comes from adiabatic observations. And as you see, as I compare theory to data, we see exactly that pattern. And here it is with the Planck data. Here it is with the data from the Atacama Cosmology telescope. And you can actually test different models because you get different patterns. If there was no dark matter, we would see something that looks like this. No dark energy, we'd see something that looks like this. Our standard pattern predicts that temperature pattern, and what we observe looks just like that pattern. So now let me turn to see where we are currently with the model. And here I want you to take away that we're seeing these patterns of sound waves, not just in the temperature measurements, but also in the polarization measurements and in the large-scale distribution of galaxies. And what has happened over the past 50 years is something that Rashid Sanyayev and Yakov Zoldovich in their 1970 paper talked about, where they said we can do a detailed investigation of the spectrum of fluctuations, may in principle lead to an understanding of the the nature of the initial density perturbations, since a distinct periodic dependence of the density of perturbations on wavelength is peculiar to these adiabatic fluctuations. And we have seen, exactly what they predicted. Here's a paper, some recent results from 2020 from the ACT telescope, where you can now see that we pushed out in polarization as well as temperature out to multiples close to 3,000, which corresponds to an angular scale of about 1/10 of a degree. This is data that the ACT team reported about 4 years ago. The team of which I'm part has continued to collect data. We now have much improved data. We're over half the sky. We have 5 times the precision of the Planck's experiment with 5 times the angular resolution. We have analyzed the results, so I have much better points than these. Because we have not yet released it, I can't talk about it, but stay tuned. There will be a better version of these figures and a better version of these measurements. And you will see as the data continues to improve, do things keep fitting? And that to me has been the really exciting thing to be the theorist involved in these experiments, because the data keeps improving, and each time we don't know if the model will continue to fit. And will we see evidence for new physics? So that's a teaser for what will come. I'll note, in addition to the sound waves we see in the microwave background, the same pattern of sound waves. Those sound waves coming up means that if you look at the distribution of galaxies, look how they're correlated, there's an excess of galaxies where those sound waves move. And this is the 2-point correlation function measured in the Sloan Digital Sky Survey data. And you can see these sound waves in the sky. And this is after one removes large-scale motions using techniques that Dan Eisenstein and I developed. You can see this is working with the Sloan data. You can see this, and we'll look at the most recent data shortly. Here's a summary as a bit, roughly a decade ago, the Planck team showing the distance measurements, and what has happened over the last several years is experimentalists, realizing the power of these acoustic fluctuations, are conducting bigger and bigger surveys to see what's going on. The largest reported results are coming from the DESI experiment. Euclid is up flying now, making its measurements. We should look forward to seeing those soon. This shows the current state of the DESI results. This is a measurement of distance versus redshift, where the curve shows predictions from Planck. And the points are shown here. There is a lot of excitement, or something, a little bit of excitement, over that yellow point being high. I'm reluctant to jump on that bandwagon at the moment because the red point is low. And 2 sigma things happen all the time. But I think the overall message you should take from this is the consistency between all the models. You could also express this in terms of cosmological parameters. This shows a measurement of this acoustic scale. What this scale is versus the density of matter in the universe in curve. The purple curve shows what we infer from the microwave background. The other 2 curves show what you get measured from the DESI experiment and the Sloan experiment. And what I want you to take away from this is not only are we measuring parameters in this cosmological model with enormous precision, that we're seeing consistent parameters through multiple methods. Another method that I'd like to talk about that we have some new results to report on is another technique that makes use of the cosmic microwave background. But now we're not using it as a snapshot of the universe 13.8 billion years ago, but taking advantage of the fact that those microwave background photons have to propagate from then to now. And as they do, they pass through all of the intervening matter. And as the photons pass through dense regions, what general relativity tells us is matter curves space. So as you move through a dense region, you get deflected. And the pattern of temperature and polarization fluctuations get distorted and affected by all the intervening matter. So we can use this to infer the large-scale distribution of matter. And this figure here, I think this one is the large-scale distribution of matter inferred by the microwave background. And this is the large-scale distribution of galaxies inferred from infrared emission from the Planck satellite. So this is how stars are distributed on the largest scales of the universe. So this is a slice across the entire sky that's about 10 degrees wide and goes across the sky. That's how the matter is distributed. And if I line the plots up right, they're basically identical. On the largest scales, light and matter trace each other. And we're actually seeing the large-scale distribution of all the mass of the universe projected. And we can then quantify this by looking at the lumpiness of the universe versus scale. The curve here is a best fit to the Planck data. We take the Planck temperature data, which tells us what the universe looked like 13.8 billion years ago, and how lumpy it was then. We take our theory, we predict how lumpy the universe should be roughly 2 billion years ago, the time at which were the characteristic distances 2 to 5 billion years ago that we're looking at with the microwave background. And the red points show the recent ACT lensing data, measurements of lumpiness. And again, you see the data fits the theory. The universe is as lumpy as we think it should be. And it evolved over that 10 billion year period as we expect it to evolve. So we seem to have a consistent theory. And this shows the wealth of observations that we now have of microwave background measurements from experiments from Chile, the South Pole, and space with Planck. And the data continues to improve since we made these first observation fluctuations back in 2011 with the ACT experiment. And as we look towards the future, they'll continue to improve more. There's been a lot of excitement and attention over the past several years about measurements of what's called the Hubble constant, the expansion rate of the universe. And it really comes down to a bit of a tension between measurements using those sound waves of rulers, those sort of standard physics-based measurements, which tend to get expansion rates of around 68 kilometers per second. And measurements of a distance using classical astronomical distance ladders, and in particular, measurements using Cepheids, which are the most precise, which are the points shown in orange. And you'll see those orange points have an average value of around 73. A lot of those measurements have been led by a team led by Adam Rees and collaborators, and hundreds of papers have been written on theoretical explanations of why those two are different. There's been recent advances in observations, and these are results reported by Wendy Friedman and collaborators in a recent paper that appeared on the archive that shows their best measurements using different techniques, using tip of the red giant branch measurements, fluctuations in luminosity, Their combined best measurements have values of around 69, very much consistent with the microwave background measurements of 68. They also get a measurement using Cepheus that is consistent with Adam Rees's value. So you notice the blue curve, which is their Cepheid measurements alone, has a value in the 72 to 73 range, consistent with what Rees has said. This is something where I think future observations will help, to explain what's going on. If Adam Rees was here, he would tell you that the Cepheids have been the most studied and most reliable. If Wendy Friedman was here, she would tell you that Cepheids sit in the plane of our galaxy and subject to dust and more systematics. If they were both here, it'd be entertaining. I've been to those meetings. My own view is to actually at the moment be impressed by the consistency with our microwave background measurements, our measurements of galaxy distribution, and our measurements with James Webb that Wendy Friedman has led. And to suspect that the errors in the Cepheids have been underestimated, and that it's a difficult technique. It's hard to get absolute distances in astronomy. They have been wrong before, and we will learn more in the future. There's also been interesting discussions of the amplitude of fluctuations. And again, question, here, measurements of how lumpy the universe is versus scale, with smaller amplitude measurements coming from large scales, lensing measurements and from galaxies and from the microwave background. Here, I think the resolution is astrophysical. We see evidence from our microwave background observations, where again, we can use them as a background to look at the large scale distribution of electrons, and see that we're actually seeing winds blowing galaxies, gas out of galaxies. We'll skip through this for now and turn to probing the early universe and talk about what I see as one of the next frontiers in the field, one of the next set of big questions. I'm motivated somewhat by the fact that the observations of polarization that are being taken here or up there at Skinaka Observatory, I think will be an important complement to making our microwave wave observations to see what's going on with probing the early universe. So we know from the temperature fluctuations that whatever generated the fluctuations is something that happened on very large scales. When we look over there and we look over there, we see correlated temperature fluctuations. In the standard expanding universe model, those were never within the same scale. So how do we produce things that are correlated on those large scales? Our best current idea is the universe underwent a period of exponential expansion called inflation. And inflation predicts that the spectral index should be less than 1, and that's what we see in the microwave background observations. It predicts the fluctuation should be Gaussian random field, and this shows a histogram of temperature fluctuations. Top one from data from WMAP, just looking at number of hot and cold spots. You can see it's completely symmetric. We can look at measuring things like the 3-point function of the temperature fluctuations, look at other various statistics of non-Gaussianity, and everything we see is consistent with Gaussian random field fluctuations that are isotropic and homogeneous. So all consistent with inflationary predictions. So what are the big inflationary predictions? The universe should be flat, nearly scale invariant, adiabatic, and Gaussian. We see all those. The next big one is a stochastic background of gravitational waves. And that happens because during inflation, the universe expands really quickly. That rapid expansion means any massive this field gets quantum fluctuations that get amplified. And any massless field will produce fluctuations. And these fluctuations you can think of as gravitons generated at the de Sitter temperature of the early universe. So just like a black hole has Hawking radiation coming off of its edge, the expanding universe produces its version of Hawking radiation, and that's the gravitational wave. And all that sounds very theoretical and interesting, but you know, those gravitational waves will generate E and B modes. And remember, density fluctuations generate only E modes. So if we can see a B mode pattern, if we can see this curvature pattern here in the observed microwave background polarization, that will tell us that we have seen gravitational waves. And there was a great deal of excitement about this about a decade ago because of these observations from the BISEC experiment that found, reported the pattern. You look at these patterns here, you see the pattern of predicting polarization. Generated over 1,000 citations within 3 months. Problem is, when we observe the sky, we don't just see the early universe. We see the galaxy. Now, if you're a galactic astronomer, that's great, because there's interesting things to learn about the galaxy. But I think of it like looking out your car window and seeing what you think is an interesting pattern in the sky. But really, it's a smudge on the front window of your car. And the galaxy is quite close. And there's lots of dust and electrons and polarization pattern in our galaxy. And we need to observe through that to see what's going on. And in this particular case, it turned out to be just dust. As we continue to improve our data, we want, this is our chance to do it. We need to get at the dust. The next big thing that we're doing, and here I'm actually wearing both my hats, since when I started, was involved in proposing this experiment, I was working as a cosmologist at Princeton. Jim Simons got excited about the idea of funding it. I'm now president of the Simons Foundation. Jim Simons, sadly passed away this year, but was very supportive of this program. Jim was a mathematician. He's the same Simons of Chern-Simons theory. That's not where the money is. He set up a hedge fund that was incredibly successful and I think is worth about $30 billion. He put over half of that into support of basic research in math and science. And some of that went to, and he was very supportive of this, building the Simons Observatory. We got first light in March, just before he passed away. We'll get first light with the Large Aperture Telescope in 2025. It's currently the largest funded microwave background experiment, actually close to 200 million. It now has contributions from the NSF, UK, some French and growing French contributions. It's a large international team that has come together to work on this. And we're really in the process of going from detectors and experiments forward. And, we've got, I slipped in these 2 slides at the last minute after the talk this morning to show our small aperture telescopes with our dichroics. And the key thing I want to put this on is these are all metamaterial lenses that are essential for our work. And we are getting starting to get our first data. We have some preliminary observations that we've taken over the past 6 months. The other full telescope set is coming online as I speak, and we will have high quality maps of polarization. And this is one of the reasons I'm very excited about the work being done here to learn about the pattern of dust polarization in the galaxy, because we're going to need to understand that if we can achieve the full sensitivity of the microwave background later to understand the stuff in front, so we can get at the cosmological measurements, because that's what's key to seeing what's going on with gravitational waves. Let me conclude by saying one of the things I hope you're taking away for those of you from outside of astrophysics about what's going on in the field from both my talk and earlier today is we have this incredible explosion of data from observations of the whole sky at the X-ray, microwave background, optical surveys, infrared surveys, and we have this wealth of data. And I think now we need to make sure we have the statistical and theoretical tools to get full value from this. So let me conclude by saying I hope you've taken away the idea that we have these precision measurements of microwave background and molecular structure, and they seem consistent with this standard cosmological model, a universe that's both very simple and very strange. And while it's been very exciting to see progress over the past 20, 30 years in this field, the coming decades poised to be even more exciting, as we'll see better microwave background measurements, large-scale structure measurements, and as these continue to improve, we will learn more about the universe in which we live. So let me stop there. Thank you.
Thank you very much. Are there any questions? Sam?
Can you hear me?
Yep.
Okay. So, as Mr. Fantastic overview. So one thing that you didn't really mention, I was curious your perspective on is modified gravity. So, like how this fits into this perspective.
So one possibility is that when you see dark matter, it's not dark matter, it's a breakdown general. And there are different ideas for modified gravity. And the ones that are best developed have predictions, right? And those predictions so far for existing theories have failed. The most recent test that I'm excited about is one led by my former student, Spergel, where she took the measurements of the microwave background kinetic spiezodomic effects from electron routine. That lets you infer velocities of function scale. And you can stack that around galaxies and measure velocities out to 100 parsecs, 300 feet. And what you see is the gas is falling in to mass concentrations, just as predicted by that relativity. You're seeing, since you're doing spherical stacking, you can actually use Newtonian theory. One nice thing about Burkhoff's theorem is it says, if you're working with things that are spherically symmetric, don't even worry about GR. Gravity is a 1/r² force, and that's what we're seeing. And modified gravity theories require the gravity on large scale to behave differently. Otherwise, we need dark. So they can, it's an idea that continues to be worth exploring in its different forms. The ones that have been explored fail to fit the current observations when you look at them, particularly in this kind of large scale linear regime with the observations of some of these things.
In the early part, you spoke about this acoustic wave propagation. Now, to have acoustic wave, you need an elastic medium. So what is I'm not sure I understand what is the elastic medium.
The plasma of electrons and protons in the medium.
So do you know the elastic properties of the
It's actually, the early universe is easy. It's homogeneous electrons, protons, coupled by photons. And everything's thermal. So it's two thermal gases. and you can work out the sound waves and its elastic property. It's about the easiest gas to work with, because it's uniform and fully ionized. So we can, you need to worry about the detailed things like hydrogen combination rates and things, but it's hydrogen helium rates.
You have any nonlinear effect?
No. Makes life very easy, because the amplitude of fluctuations are 10 to the 5. So, the nonlinear effects are 10 to 10. The ones we can calculate are second order. So the perturbation theory effects. There are many PhD theses where people do the maximum number of effects. In the early universe, they're not micro background. Nonlinear effects become important when you start forming galaxies. And that's why interpretation of galaxy observations both more interesting in some ways, but it's harder in physics creature, but it's also hard because So one of the pleasures of focusing on the microwave background, it's linear physics theory. Most of the theory you need for this, is stuff that you've learned at some level as an undergrad.
You give some details on the second point on the constraints that the CMB will give to the neutrino mass. For example, information on all 3 neutrinos.
It'll give constraints on two interesting constraints. One on the sum of the neutrino species. So not the mass differences, but the sum. I was hoping someone would ask this because I had to remove, I would run over with my neutrino slides, so I pulled them to the back. What we'll measure is the sum of neutrino species, basically to be able to tell the difference between the normal hierarchy, where the tau neutrino mass is heaviest and the electron lightest. The experiments we have from neutrino oscillations are always telling us about mass differences, and this gives us a measurement of the sum versus the inverted hierarchy. And right now, our constraints are such that we can't quite distinguish the two, but they're pretty rapidly improving. And we should be there within 5 years, I think, where we could either detect or start to rule out the inverted hierarchy. The other thing we'll get at, which I think is very exciting, we already have constraints on this, is the number of relativistic species, because that affects the expansion rate of the universe. So if there's any other light particle in the universe, so if you have an extra Z1 that added to the theory that creates an extra neutrino species from an extra U1 you add in, we would have a background of these relativistic 4th generation neutrinos, or these are linearly not coupled to this W or Z, so these are sterile neutrinos. But they would contribute to the expansion rate of the universe, and that affects our microwave background fluctuations. It affects the peaks, and right now we have no evidence for extra species. And I anticipate with the data we have in hand, we will significantly improve that constraint. That's actually one of the things we're targeting, and that lets us constrain a set of beyond standard model physics measurement ideas.
Concerning the additional tensions, so you were considering somewhere that the supernovae calibration for
Cepheid calibration.
Cepheid calibration.
That's I blame the Cepheids.
Okay, but then there is also the time delay, quasar time delay, which also show higher H naught, right? It's not only supernovae.
It depends so the idea here is you can do a nice geometric measurement. You can have a gravitationally lensed system where you see 2 images of a quasar and they vary, and those time variations, I'm just trying to explain this idea for a more general audience, gives you a measurement of distance. But inferring the distance depends on knowing the mass structure of the lens. And the mass sheet degeneracy means you can always add mass, and that changes the distribution. And depending on the different mass models you use, you get different answers. And some of the most recent analyses actually get a Hubble constant very close to the standard value, the CMB value. So I think it depends on which one of those findings we're going to use. I think many of us have hoped that this would be kind of the clean geometric way to go. What I now think is that, my favorite of future methods is gravitational waves. And that we will, gravitational wave signal from a neutron star merger. We see the light, we know how far away it is in redshift. We can measure the amplitude of the gravitational wave signal that will give us distance. We only have one event so far. So the error bars are big enough, they're consistent with both measurements. I think in the coming decade, with improvements in LIGO, more observations, we'll have much more data. I think that will be the cleanest test.
Well, if there are no more questions, let's thank David again. Which was not saying